Technical difficulties earlier, so
You should turn down the
there we go. Good. 3D modeling, digital modeling, the representation of the world through electronic means has been around for about 50 years or so, but its origins go much, much further back. And they go back not just to the technical difficulties that have always been present in recording things, but to the way that we evolved as a species on this planet. We'll start in the dim and distant past. We've been on this planet as a recognizable species for several million years. I believe about 4 million, but obviously the exact date is open to dispute. And we've been relatively civilized for the last 100,000 or so. We've grown up in an ecology, in a system of plants and animals, which is based on various things. One of the most important distinctions in animals is predators and prey. This is a prey species. And we know it's a prey species how? Anybody got a suggestion of why this is a prey species?
Eyes on the side of the head.
Eyes are on the side of the head, exactly. This guy's game plan is to look all around, have almost a 180-degree field of view, and whenever he sees a threat or something he identifies as a potential threat, he runs away or he dives down the nearest hole. This is a predator species. He has eyes on the front of his head, and he has eyes on the front of his head for two reasons. One is that it gives him binocular vision. The difference in view between the two eyes allows his brain to form a three-dimensional representation of what's in front of him. Because his game plan is to find some prey, run after it, leap on it, and to leap on it and catch it, he has to know pretty exactly how it and he are going to relate in three-dimensional space. The other reason he has eyes on the front of his head is that he doesn't care what's going on behind him. Anybody who attacks a tiger from behind deserves all they're going to get. So what is this? This guy looks like prey. Do you think he's prey?
Not so much.
He's a predator species. He's the worst predator species there is. Very intelligent, no claws, no fangs, but a planner, a thinker. 40% of his brain capacity relates to 3D processing, to his surroundings in some respect. Very thoughtful, a great planner, but for the last 50,000 years or so, as he's been civilized, as he's lived in settled communities, he's had a problem. What is this problem? Well, let's look at one example of it. This is a cave painting from about 30,000 years ago. It's in Brazil, in the Serra de Capivara National Park, and it's a painting of a hunt. A violent, dramatic event that was probably the major thing going on in the lives of the people who lived in and around this cave. It provided their food, it provided their materials in terms of bone and skin, it provided clothing in terms of fur. But it was so important, so vital, so interesting, they put it on the wall of their cave and they had to flatten it. They had to flatten it from 3 dimensions of space and 1 of time into 2 dimensions on the wall of a cave. Flattening and freezing this vital, important event. That was all they could do to record it and communicate it. We haven't, until very recently, progressed much beyond this. When we try to communicate a form, when we try to record a form, when we try to design something, we had to do it on a 2-dimensional surface. And the cave painting became a sheet of paper, and papyrus, became a flat computer monitor, didn't change it. We were trying to develop 3-dimensional forms, 3-dimensional processes through freezing and flattening it into 2 dimensions. As Jen said, I started in architecture. I learned architecture, well actually I began in physics and math. I transitioned to architecture after a year or two in the early 1970s. This was what I used for calculation in my physics labs, a slide rule. A slide rule that could have been used by somebody 1,500 years earlier. Indeed, if they'd been taught, it could have been 5,000 years earlier. Nothing changed very much. The paper, the drawings, the mechanical calculations, and in the last 50 years, everything has changed. I show this to my students at UCSC, they don't know what it is. We've gone three-dimensional computer modeling has changed not just architecture, but engineering, animation, movies, the way we see the world. And what I'm going to do this evening, in the next 40 minutes or so, is give you an idea of some of the ways that three-dimensional computer modeling has changed and is changing the world around us. This is a CNC machine, computer numerically controlled mill. The design that we see in the previous drawing, this is a drawing of a mechanism done in SolidWorks. This design could be sent to this particular mill and it could be cut away from solid materials, a subtractive process where most of the workpiece ends up as dust and shavings and waste on the floor of that machine. There's now a new process and it's called additive manufacturing, and we're going to look at that very shortly. But first, let's look at a different aspect of 3D computer models. Computer animation. Animation's been around for around 100 years or so. Computer animation has been around since really the mid-1980s. The first significant computer animated movie, it's short, it's only a couple of minutes long, was made by Pixar. Or rather, it was made by the founders of Pixar before Pixar became Pixar. It was used as a demonstration of the way that 3D computer models with artificial lighting, with animation, could be used to tell not just a story about an engineering product, but a story about characters. Let's have a look at that. I'm going to have to go over here.
Probably took weeks to compute it all. Now bear in mind that until this was made in 1986, computer animation had only shown mechanisms. It had shown architectural models. This was one of the first animations, computer animations, to communicate character and situation and personality using all the techniques of traditional animation.
That's actually one of the animations I used to teach in UCSC, because it's got all the principles of animation, all the 11 principles of classical animation in those 3 minutes. Very vividly and well demonstrated. Pixar, as we all know, went from strength to strength. Toy Story, 95. Toy Story 2, 99. Other studios were starting to build upon Pixar's experience and success. Toy Story 3, 2010. Every time, getting better and better, using more accurate lighting, more interesting characters, more advanced animation techniques. But at the same time, computer-generated visual effects were also appearing. Computer-generated visual effects were originally fairly simple. Terminator 2, probably most of you here have seen that. Groundbreaking special effects, the liquid metal man who could rise from the floor, who could walk through a grating, who could emerge from flames. That was one of the first examples of convincing, powerful visual effects made purely through computer-generated means. 2012, in 2009, Inception, 2010, we've got used to seeing these, and we don't realize they're not real anymore. It started to become part of our reality. Let me show a video here which makes it clear exactly how powerful this technology is. Screen here is pretty much an empty field with a couple of blue screens on it. What's being filled in from the base is computer-generated image. Again, blue screen behind the actors and some detailed set. And you fill in a computer-generated house behind you. That again. A busy street full of lights, motion, buildings, and none of it's real. This scene is being shot with half a dozen vehicles from the local museum, a couple of dozen extras, a few stars, and yet you can film in an entire city around it using purely computer-generated means. This is how most films are made these days. Very little of what you see these days is real. Again, one actor or one musician against a large blue screen in a studio. Must be tough for the actors. They're trying to act as if they're in front of a large house or in a city surrounded by movement and light, and yet they're in an empty studio surrounded by blue curtains. So visual effects, animation, What else are 3D computer models doing for us these days? Well, the thing that's in the news a great deal these days is 3D printing. And I'm going to look at a few of the printing technologies, again, all based on 3D models, which are around. This is our CNC milling center that we looked at a couple of minutes ago. And you'll remember that I said it uses subtractive technology. It removes material from a workpiece. And that can be a workpiece which is made out of steel or plastic, sometimes a ceramic material, but basically it's actions that cut things away or grind things away. That's been very good, but it's not everything. There are many things you can't make purely from subtractive operations. One of the things you can't do is you can't shape internal cavities unless you make that item in several pieces, and maybe for strength reasons, maybe for other reasons, you don't want to do that. You want to make things from a single piece of metal. You can't make an internal cavity, for example, like this. You can't make a helical hole through a block of metal using traditional technologies, no matter how good your machining center. You have to make it in several parts. This is the first 3D printer, and it's dated around 1984. This technology is about 30 years old. It's been kept in large manufacturers, in universities until now, because the machines and the technology is slow, imprecise, the equipment is expensive, the technologists, the people who are trained to use it need a good deal of skills. About 5 years ago, it started to come out of the laboratory. And part of the reason it did so was because of the fact that people realized that now it had reached the stage that it can create impossible or unaffordable objects. This is a ceramic sculpture made by the Santa Cruz artist, Sheba Grossman. She designed it in a 3D program called Rhinoceros, and it's been printed out in ceramic powder, been fired, been glazed. It would be impossible to make this by hand. Imagine somebody trying to carve this out of a solid piece of unfired clay. It would crumble. Imagine them trying to shape and place pieces of soft clay to make something like this. It could never be as accurate. This is a form that would be previously impossible to make, and even if somebody spent a lifetime carving it out of jade or of bronze, it would be incredibly unaffordable. Bathsheba sells things like this, 3D printed for between $80 and $120. They're 3D printed, they're not mass produced, they're produced in batches, but something like this, as I say, would have been impossible or unaffordable to make even 20 years ago. This is a Klein bottle. I don't know if we have any mathematicians here, but a Klein bottle is a shape with one surface. She made a Klein bottle opener. And this Klein bottle opener is available, actually I think MakersFactory sells them for $80. Another interesting thing about 3D printing is that it can not just make impossible or unaffordable objects, it can make mechanisms. This is what's called the brain gear, and it's printed using a different technology to the one that Bathsheba Grossman uses, but very similar. It's printed in ceramic powder. And this is a brain gear that was printed at MakersFactory about 2-3 years ago. And you can see several things about it. First, it's in color. This is 3D printing in color, bright, vivid color. The second is that it was printed in one piece. All these gears have a little space between them and the axle that runs through them, so that as the 3D printed part is built up in the printer, the unused powder separates the components and it can be blown away with compressed air once the job is finished. I'll show you how that's done in a minute. This is another piece that's 3D printed. This was done in several pieces. Again, working mechanisms and color from a powder printer. This is the powder printer that we have in MakersFactory. There's a second one back here, a simpler one. And I'll show you a video of this one in operation in a moment. But let's concentrate on this one first. There's another view of the device. And there's a large build chamber on the left-hand side where layers of powder are laid down and glued together either with a clear binder or binder with colors. Take it out. There's a depowdering station here where a compressed air gun is used to blow away the unused powder from the finished print. And this is the process. We start with a 3D model. And you make your model in any one of a number of different softwares. One of the interesting things these days is that some of these softwares are now free. They're open source and free. I teach at UCSC using a program called Blender, which is excellent. It's as good as a $4,000 or $5,000 program would have been 5 years ago. But it's free, it's open source, it's reliable, and it's excellent.
Would you move the mic a little closer, please?
Oh, I'm sorry.
Thanks.
So you have that 3D model. You put it into slicing software. And the slicing software slices the model into horizontal sections, which are the thickness of the layers of powder that the machine lays down. And these layers of powder vary between about 1/10 of a millimeter and about a 20th of a millimeter. That's about 1/250th of an inch to 1/400th of an inch. So about the thickness of a sheet of paper. These layers are then sent piece by piece to the printer, and as the powder is laid down, the layers are glued together according to those slices to produce a finished 3D model. Let's look at that again on a video. And this is a fairly old video, but it does very well for demonstrating the principle of powder printing. Here, the printer driver is importing the 3D model from the computer program. And this is a model of a ball bearing. The person who made the 3D model was careful to leave spaces between the bearing and the little balls inside it. And the reason for that is that you want those to be filled with unglued powder so that it can be blown out once the printing is complete. As I say, this is a fairly old video. It shows a Z Corporation 450 machine, which you had to fill by hand, but it's actually good in this case because it makes it very clear what's going on. Later generations of machines do this automatically. Now the roller head here is spreading a thin layer of powder over the build plate. And it's important to understand the distinction between the two sides of the machine here. The left-hand side is about 8 inches deep, usually, filled with powder. And it's got a base which can be raised. The right-hand side has a plate which is at the top of its travel, also about 8 inches. And layers of powder are laid over it. The cross-section is glued, and then the base goes down by the thickness of the layer of powder you want. And as I say, that's typically about 1/10 of a millimeter. You have to lay down a few layers of powder to begin with to get a smooth surface. Obviously, it's very important to have a smooth surface. And that's it. Looks like a sheet of paper. And now what happens is that a standard inkjet head sprays not ink, but a kind of glue
onto that layer of powder. And it solidifies the powder, which has been sprayed with glue. The rest is still loose. Another layer is spread over. Another cross-section is printed. So as this goes on, the right-hand side of the powder printer goes down, always with layers of powder on it, and a three-dimensional cross-section, an actual copy of the three-dimensional form made in the computer model, is built inside it. And it's all inside the powder. You just see the top layer of powder. You don't see the object itself until you finish the print, you reach your hand in, you bring it out, and you blow off the unused powder. In fact, it's not incredible speed. This is quite a slow process. Generally about an inch an hour. So if you're using the full height of the build chamber, if you're making an 8-inch high model, that's going to take 8 hours. And then you've got to wait for it to dry. That's maybe another 3-4 hours. You've got to dig it out. You've got to blow it off. It's labor intensive. Whatever you're printing, whether it's a plastic powder, a metal powder, a ceramic powder, the unused material can be mostly reused. So it's a very efficient process. You don't get most of your workpiece ending up as shavings or grindings on the floor of the shop. Video there. The process has become faster since then. It's become more automated, and also things like color have been introduced.
It's like a contra foundry.
It is, yes. It's a backyard industry. This is another type of 3D printer. This one sprays out materials from inkjet heads. And the interesting thing about this one, these are some samples, is it's called the polyjet technology. Up to 14 different materials can be printed from the print heads at any one time. This particular printer prints items about 1 meter, 3 feet wide or so, but they can be rigid, they can be colored, they can be transparent, and they can also be elastomeric. You can produce parts which are rubbery, which have backbones in them which are rigid, so you can make prototype parts of designs, different colors, different translucencies, different viscosities or different hardnesses, different resilience, all in one operation. This is the future. This is how things are going to move forward. Eventually there are going to be parts which will be produced using materials which are conductive, which are capacitive, which are semiconducting. You'll be able to print electronics into plastic parts so that you can have machines which can switch themselves on immediately they come out of the printer. It's a very exciting technology. Currently we don't have semiconducting materials, we have these digital materials. High temperature, opaque, rubbery, elastomeric, dental material, transparent, and also biocompatible, so that implants or extensions or prosthetics can be printed precisely to the person and the situation where they need it. Here's an example of a prototype piece which has been printed using several different materials. Rubber-like material here, white rigid material, a flexible material at the joint here. So this opens up enormous
possibilities for industrial designers. I was an industrial designer for 8 years. And if I had a machine like this where I could test my designs not in weeks but in hours, I would have been a much better designer. My clients would have had much better products, and everybody would have been happier. This is an enormous improvement in design capability, not because it makes better designs, but because it allows you to iterate faster. And as a designer, as any type of creative person, it's the iteration, it's the assessment and the improvement and the repetition that makes the perfect result. This is a different kind of 3D printer. This is a laser sintering machine. Laser sintering machines print metal. This is an example of a laser sintered piece. This is a piece that I designed myself about a year or so ago. And it's partly printed in alumide, which is a mixture of nylon and aluminum powder, and partly nylon. This would have cost hundreds, if not thousands of dollars to produce from a conventional machine shop. I got this in a week from Shapeways online, and it cost me a couple of $100. I was able to check the mechanism, I was able to find the problems with the way it worked, I was able to improve it, move on to the next iteration very fast and relatively cheap. Laser sintering machines operate with plastic powder and metal powders. So that, sorry, question?
Oh, what does that thing do?
This is part of a continuously variable gear that I got a patent for a couple of years back, and I'm still working on prototypes, so I can talk about it later. So this is the kind of machine that Bathsheba's metal bottle openers would have been printed on, using bronze powder. You can also use titanium or steel. You can use nylon powder, various other kinds of plastics. But the thing about a laser sintering machine is that it uses a laser to sinter together layers of the powder, rather than using a glue to glue together cross sections. It's the same process. It's the same rolling of a powder into paper-thin layers. It's the same gluing or fixing together of cross sections. But in this case, it's done by a laser. And because powdered metal and plastic, and indeed almost any material, is explosive when it's in a fine powder form, it has to take place in a inert atmosphere, generally argon. So these machines are expensive. Close to $1 million for most of these. You have to be putting material through very fast, continuously, pretty much on a 24-hour cycle. Laser sintering, cross-section of the machine, or diagrammatic view of it. The laser takes the place of the inkjet. There's the roller on the right-hand side there, simply rolling layers of this very finely divided material, could be steel, could be plastic, over the print bed, which, like the inkjet technology, sinks down slowly into the body of the machine.
I have a question.
Mm-hmm.
Do you get full density with that, or is it a porous?
It's generally granular. No. These bottle openers here that Sheba Grossman designed go through a two-part process. So the granular bronze print is impregnated with a lower melting point metal afterwards.
Okay.
So it kind of wicks it through.
Sort of like a cementing.
Yeah. So it's actually an alloy.
Yeah.
But you get something with the weight and the appearance and the machinability of a solid metal piece. And finally, the simplest technology, FDM, fused deposition. This is a recent FDM printer. In fact, I have one of these myself. And produced by PrinterBot, it shows very simple technology. These things are pretty much 3D printing, stripped down to the basics. These don't use powder. What they use is a plastic filament which travels through a heated extruder head here and is deposited on a bed. This bed moves back and forth. The head moves in and out. So between the two of them, they can trace out a cross section. And then the extruder head moves up slightly based on the action of this screw, another layer is printed out, and you end up with something like this. This was printed off my own machine a week or so back. Part again of a prototype. Actually, we could hand that around. Some other pieces here. And you can see that the finish is not perfect, but they're quite strong. The material is generally ABS or PLA, polylactic acid. Quite strong, resilient, so you can make working parts. You can make gears that actually work. And you can do this on your home, on your desktop. Much the most accessible of the technologies. This is where the future, probably, of home 3D printing lies. Though I'm actually a skeptic about home 3D printing, because the main thing is that you actually have to know how to make a 3D model. 3D models are the basis of everything here. They're the basis of structural analysis, they're the basis of animation, they're the basis of effects, they're the basis of 3D printing. So the fundamental skill in all this is not just design, it's the ability to use a 3D modeling program. As I say, modeling programs are now becoming not just cheap, but free, but all the problems of learning them are still there. But it's a necessary part of 21st century digital literacy. These are some other parts printed out by a fused deposition printer, an extrusion printer as they're sometimes called. And we can see a couple of the drawbacks. The finish isn't particularly good. You can only print in one color. You can't print a mechanism because the strands of hot plastic will glue up the mechanism, but you can assemble various parts to replicate that mechanism. 3D printing applications. So over the last couple of years, new technologies have emerged in the 3D printing area, which are quite interesting. This is the Cerajet. This is a 3D printer for ceramics. It takes clay powder, does the same kind of thing as the Z Corporation machine does. It glues sections together, paper-thin sections, gradually builds up a 3D form, which you can then take very carefully out of the printer, put into a kiln, and glaze. And you can make the kinds of ceramic form which would be impossible to make by hand or by a mold. Imagine trying to mold something like this or make this by hand. Simply be impossible. Again, this one, you've got internal detail, which couldn't be done any other way. And in fact, that's a good point about 3D printing in general, that there is no cost to complexity. You can make a model which is incredibly complex, externally and internally, and it costs no more, and it takes no more time to make than a simple cube or a sphere. This is another new printer just come on the market, the ChefJet, and that prints sugar. Not as trivial as it sounds, in fact, because much of our experience of tasting something, of cooking, is the texture of what we're eating. So being able to 3D print a new type of candy, a new type of pasta, a new type of cookie, is not only going to affect the look of it, it's going to affect very subtly the taste of it as well. So many, many interesting things are going to come out of this particular technology, I think. These don't look particularly attractive, but you never know, early days yet. 4D printing. Has anybody heard of 4D printing? Look at that. So 4D printing is 3D printing with the added dimension of time. The ability to take a model which has got hinges and mechanisms to lock it into place, fold it up, print it in the build chamber of a 3D printer, and then when it comes out to unfold it and either have it as something which is permanently flexible, or something which can be glued, or using internal mechanisms, be locked in place. This again is part of the future of 3D technology, 3D printing technology. Something that NASA is very interested in right now, because when you're taking a 3D printer up into space, you don't have a great deal of volume. You have to have a printer with a fairly small build chamber, but they want to print structural elements. They want to print replacement parts for items that get damaged. So the ability to print something small, unfold it, is very interesting to them. Here we have a dress. 3D scanning. 3D scanning technology is another one that is rapidly advancing. You have your form, you tessellate, that is, you tile your form. Generate a mesh. This is a fairly coarse mesh. I think this would be rather cold to wear. But imagine this reduced in size 10 times or 100 times. And it becomes more like a knitted fabric than a mechanism. Fold it up, still in the computer model, and send it to the printer. This company has a website where you can design your own jewelry that will conform to your model. So again, customization. Customization is becoming increasingly important for consumer products.
I don't see the website. What is the website?
Nervous.com.
Nervous?
Here.
There it is.
Nervous with hyphens between them.
Okay.
.com, get it out.
All right. Do you want me to
So trends and the future.
machine?
This is a piece of 3D printed structural steel. And it was designed by the engineering firm Ove Arup. It's the kind of element that we may see in buildings in the very near future. And it's based partly on the structure of a bird's wing. This is the interior structure of a bird's bone in its wing. And we can see that this is mimicking, this is using the same principle of precisely placing material where the stresses are in the part. Not only that, but it replaces something really rather ugly. This is what that part is replacing. It's a welded steel part. The welded steel part is not only extremely ugly, you'd want to hide that, it's also weak, because the welds themselves under stress can tear and break loose. These don't. So structural forms in steel will probably change a great deal based on 3D computer forms which are optimized using algorithms to detect and change that form related to the stress that it will undergo. This is a scientist from Yale University holding up a 3D printed plastic piece. And this plastic piece has got an unusual pattern of holes and walls in it. And the reason is that it's designed to deflect microwave radiation. It's designed to take microwave radiation coming in from one direction, deflect it around itself, and reform it on the other side. And the reason that he's doing this is because this is the key to cloaking technology. This is how you will make something that will bend light around itself and reform it on the other side, so that anything inside that cylinder will be completely invisible. 3D printing is the key to this. This is a 3D printed cloaking device, printed in metal, not for very short wavelength radiation, mostly microwave radiation. We haven't got anywhere near cloaking technology for light yet. But when we do, this is probably going to be something like the result. You'll be able to put on a jacket and disappear into the landscape.
Great for stalkers.
Architecture. Architecture. The Walt Disney Concert Hall in Los Angeles, designed by Frank Gehry. Again, using the computer program Rhinoceros, it could not have been designed on paper. This had to have been designed in a 3D computer program. But it was manufactured using relatively conventional technology, cutting and shaping and assembling on site by hand. Things are changing.
That's what I want to do, is print a house. We need a really big printer.
How far away are we?
There's a group at USC which is developing extrusion printers that print using not hot plastic but cement. And it's a tough thing to do, because you have to develop a material which is liquid enough to come out of the nozzle, but rigid enough to stay in place once it's put onto the preceding layers.
Modeling clay.
Also, it needs to harden sufficiently fast that the layers underneath don't start to slump because of the weight of the material on top of it. But they're doing it. This is an example of an early prototype, a maze, showing the extrusion device they developed.
It's hard to do on a potter's wheel.
A larger device, printing concrete this time. A further development where you have 3 extrusion heads, 2 of which operate at once, printing the sides of a wall, the faces, and a third which goes and prints reinforcement inside.
Concrete,
So
cardboard.
this is a 2-stage process for each layer.
Wow.
Probably wouldn't pass California earthquake code, but I'm sure they will.
I think it's brittle.
So you can print walls which are not just straight, but curved. And you can print them not just in a factory, but on site. This is a rather bad animation, demonstrating the technology.